Okay, welcome back. We assemble for the second talk, and a very interesting one on plasma turbulence at the edge of fusion reactor by Rupak Mukherjee. So Rupak, I know him for now, I think for several years. So Rupak did his PhD from Institute for Plasma Research, IPR, and then he moved to Princeton, PPL, and he's working on plasma-related simulations, and he has developed uh, interesting codes when GPUs and so on. So he has skills in physics as well as in computing. So he's going to tell us about his work today. So Rupak, please take over.
Sure, thank you very much. And also, it's a pleasure to see some of the known faces, known people here after quite a few years. So anyway. Okay, so I initially planned the talk for the early students. So the very beginning part of my talk will be pretty much simple and probably obvious for many of you. So you can actually tell me to fast forward if you're feeling that I'm going too slow. So, okay, thank you very much for giving me the opportunity. I will be speaking on plasma turbulence. And this plasma turbulence occur in different cases. Most of you are probably familiar with plasma turbulence in astrophysical scenarios. But here, at least, we are doing it in a fusion reactor. So we have a fusion reactor in Princeton and in Germany and in many other countries, including India. And plasma turbulence do occur in these fusion reactors because we achieve the fusion via plasma. And why do we need plasma, etc. That I will be talking about. Okay, somehow, good. So this is just a cheap and quick overview of why do we need fusion, because you know that we need to spend a lot of money on buying the fuel, etc., importing the fuel from other countries for our energy. So basically, we need to be energy independent as soon as possible. So to save our expenditure on energy, because anyway fossil fuels are running out, so we need to build something which is renewable, or like we have enough amount of energy stored, and the fusion is a good candidate for that. So that's it. If we think that how did we spend our energy over the last 1 or 2 years, you'll see we have spent most of the energy by burning coal, etc. So we need to increase this thing, we need to go more on this renewable side, on the contrary to this coal-based energy. Because these are fossil fuels and we need to change them. Also, it's not very good to be carbon, like energy by burning carbon, etc. Well, by burning coal, etc. actually increases the global temperature. So it's better to switch to something alternate. Solar is definitely a good candidate, but the conversion efficiency is not very good. So it's not very reliable, because some day can be sunny, some day may not be, and we cannot store power for very long, so it's very costly. So here, as I am saying that why fusion is needed, because it's a long term, it's pretty much safe, and it's green because it does not emit any carbon. Green solution within 50 or 60 years. Why is it needed? So it's fusion. Fission is radioactive, so and also it's dependent on the ampleness of the uranium and other quantities. So, but the amount of deuterium and tritium that we already have stored in our Earth from seawater and salt deserts, that's it's really a big number. So we don't really necessarily need to worry about that. So it can, if we, the way we are consuming now, if we consume it even with that, you can be sure that it's roughly like the total amount of fusion energy that we can produce out of it is 30 times more than the lifespan of the sun. But achieving fusion has some technical and as well as physics challenges. So the idea is, what can we do for that? Okay, so what are the technical questions in achieving fusion? At least one or two of them I will address, and I will talk about how we are trying to solve them. So first of all, we need to learn how do we do the fusion, and before that, probably we have to see where fusion happens in the nature. The fusion happens in sun. So the question is, why can we not learn from sun? The temperature at the core of the sun is somewhat this number. It's like 1.5 into 10 or something. So you can see the temperature of a flame is pretty less. It's 1,500 degrees centigrade. And the fusion devices that we generate in laboratory, that's even hotter than the core of the sun. So definitely this temperature is not achieved just by heating up water or some vapor by flames, because this is pretty much cold than this. So we need more physics insights and more engineers to carry out those physics ideas. Definitely we have different technologies like ohmic heating. You know, if you run a current in a loop, it causes ohmic heating. We do launch different waves like electron cyclotron resonance heating, ion cyclotron, NBI, etc. So what does sun do is sun basically fuse the hydrogen there at this temperature and it produces energy. So why can we just not do the same? Question coming back again. The problem is, in the sun, the plasma is confined, while in Earth, there is a problem in the confinement. Now you can ask why the plasma is confined in sun. Plasma is confined because the plasma is confined mostly within the sun's radius. So the question is, why does our sun have a radius? Why is it not just all pervaded in space? Because it's massive. It's just it has a critical radius. You can work out from the Chandrasekhar limit, or like for a star, you can work it out. So it's just basically the gravitational attraction that keeps it that gives is a fixed radius. But in Earth, we cannot have that much of gravity because it's not that massive. The plasma that we generate, it is not that massive. So we need to confine the plasma in this Earth to achieve the fusion. But how will you confine? Now, in a plasma, basically, all of you are already probably familiar with the plasma because it's a collection of charged particles with some extra properties. So now, if the particles are charged, and you know the motion of a charged particle in a magnetic field. So if I have a magnetic field, the motion of the charged particle around either helical or it will be like circular. So effectively, if we have a magnetic field, which is like something like a circle, closed circle, and if you just throw one single charged particle, it can just simply keep moving in that magnetic field, and it can be trapped. Right? Okay, so we actually do that. We create a twisted toroidal magnetic bottle in this laboratory, in our laboratories, to confine plasma. So there are different kind of twists and toroidicity. Depending on that, we have two concepts. There are actually others, but these two are mostly celebrated recently. One is tokamak and the other is telluric. So this should do the fusion then, but it's still not commercially achievable. Why? The drawing is, when I said that you just make a circle of like a circular magnetic field, it's not that easy because there will be other drifts, etc. We have to create an optimized magnetic field structures so that these kind of charged particles can stay inside that magnetic loop or magnetic bottle. So think of it as like a rope, a lot of ropes that are going like this, and then coming back and ending itself, and then there may be some kind of helical ropes that are coming out and joining it there, and you throw the charged particles there. And remember, we are doing this experiment on Earth. So, and the temperature at the core of this magnetic bottle, this kind of structure, at the core it is like 10 times the core of the sun, and outside it's just like the room temperature, 27 degrees. So there's a huge temperature gradient, and so we have to make a foolproof magnetic bottle so that the plasma do not actually spill out from the magnetic bottle and actually touch the metals that is surrounding. I will talk more about that. That's the main part of our work. But before that, let's get back and try to understand how do we actually plasma. I'm going to talk more about this confinement structure. So now let's concentrate on this very, very simplified cartoon. Imagine a stainless steel torus. So this is the torus. Can you see my cursor just in case? Can you just somebody unmute yourself and?
Yes, we can see it.
Yes.
Oh, great. Thanks. So imagine a stainless steel torus. So this is the stainless steel torus, this one, like a bicycle tire, lying horizontally, and current carrying poloidal rings. So these are the poloidal rings. Forget about this thing, toroidal field coils. This poloidal rings generate the toroidal field. So that's why this is. So these are the poloidal rings like this around the torus and a vertical solenoid. So this is the solenoid. You see, this is some old concept of iron core. Now people have different things. So this is the very first concept of a tokamak. So vertical solenoid through its central axis of this circuit. This is the basic engineering. And what next? How do you produce a plasma? What do you need to do? Let's feed hydrogen gas, no plasma, into this at low pressure in the torus. So in this torus, you feed hydrogen gas and run current through poloidal rings. So these are the poloidal rings. Run current through this. What this current will do? This current through the poloidal rings will create a toroidal magnetic field, right? So the currents through this poloidal field, these poloidal rings, will create a toroidal magnetic field. This kind of magnetic toroidal magnetic field. This one, and ramp up high current through the central solenoid. So this is the central solenoid. Typically, it's ramping down. I mean, like it's just we need the change of flux. So that's it. So you charge this up and discharge it very fast. When it's discharging, that's good enough for an engineer's perspective. All set. Let's understand what will happen. So when you ramp up high current to this central solenoid, or ramp down, whatever, change of flux through the torus. So if there is a very sharp change in the current, in this transformer core, there will be very fast change of flux through this torus around this, and this will generate a EMF. So induce a toroidal electric field via transformer action. Okay, so we have got one EMF generated, which is a toroidal electric EMF in this pipe. Now we have fed neutral hydrogen gas. There was no plasma. However, the gas had some stray electrons. You know the numbers by Shah ionization equation. So it has some numbers, and those free electrons will generate a toroidal current through this. Okay. And the electrons will gain momentum because of the EMF. They will create further ionization, avalanche, and they will create a plasma. Like further collisions and ionization. This process will keep going, and this will create a plasma in this thing. Okay, so we established a plasma from here. Now we have a toroidal current here. We have a toroidal current. So because of the plasma, because the EMF was in this direction, and the plasma the particles are moving in this direction. So the toroidal current that is moving here, this plasma current itself will generate a poloidal magnetic field. This poloidal magnetic field. And we already have a toroidal field from these poloidal coils. These are the poloidal coils that will generate the toroidal field. So as I said here, poloidal rings, toroidal magnetic field from the poloidal. So we have two magnetic fields now. One is the toroidal magnetic field, another is a poloidal magnetic field, this thing, from the plasma current. So effectively, we actually have generated a helical. So if you add these two, it will be like a helical magnetic field. So it's like this. The helicity is important. It's if we have only one closed loop, then what will happen is basically the electrons and ions will get dissociated. So electrons will move either upwards and ions will then go downwards. So there will be a local charge imbalance. And we don't want that. That's why we need to generate this helicity. So this will keep the plasma stable. Yeah. Please.
One short question. So what is the rule of this transfer winding, the one which goes through the center, the orange one?
Roll.
What is it doing?
Oh, I see. If you actually charge it up and then immediately discharge it, it will generate a EMF around this torus.
I see. So that is to induce EMF.
Yes.
That's for induction EMF.
Give you the initiation. Yes. It's like ignition.
I see.
It will generate the first EMF, and once it generates the EMF, then it's like fine. I mean, the EMF will drive the stray electrons or ions in this neutral hydrogen gas or deuterium gas, whatever.
All right, got it.
And the electrons will then gain more energy, hit the neutrals, further ionize, more ions. The ions again will gain energy from this EMF, from this ion transformer core or whatever. People have modified it now. This is the very first, very old thing. So this was the concept, and still we more or less in the zeroth order, we are still running all the machines on this idea, except the stellar. So this is the theory for the token. Okay. So fusion should happen, but still now we do not have commercially viable fusion reactors. So why not? Because the plasma that we have generated here in this core that actually leaks out, and now we have a very high plasma, very hot plasma, and we have outside it's pretty much 27 degrees centigrade, and we have a metal or material. So what are the challenges? So that's why I wrote, after all this, the harsh reality is this plasma spills out and touch the metal vessel, and we cannot let that happen, because if we actually want to make a commercially viable fusion reactor like ITER, if probably most of you know, but still it's an international collaboration happening in southern France. It's a big tokamak, world's biggest tokamak that's being built with a lot of budget. You can just check out the numbers. It is supposed to generate 100 megawatt of power. Sorry, in this, it's pretty big. In this heater, the plasma that is coming out, that will come out, that is predicted from this, that will spill out this thing. That plasma, the energy of the plasma will be 100 megawatt. So that 100 megawatt of plasma needs to be handled within a narrow channel of 1 millimeter. So it's like when it will come out, when it will touch the metal vessel, the area in the metal vessel, it will just be around 1 millimeter. While the extraction nozzle plates or technical word is diverters. The diverters can withstand just a 30 megawatt per square meter power at the best. So this is so more research from the material scientist perspective is needed, so that we can build better metals or materials that can withstand a very high peak load. That is one option, of course. And we physicists are trying to propose something else to at least help it. But you can see clearly there is a huge difference of number. It's like it's pretty big. It's, the present day best materials can withstand 30 megawatt of per square meter power. Well, we need to channelize a 100 megawatt of power within 1 millimeter thickness. So it's huge. And this machine is pretty expensive. Its projected cost currently it is being built in 2025. It's projected US projected its cost around $65 billion. This number is pretty big. To give you some idea, I can tell, like the LEGO project, it took $1.1 billion, and the LHC, it took 4.3 or $4.2 billion. So now you can see how expensive this is. ITER is proposing $65 billion. It's a big number. So we cannot just let the diverters burn away. We cannot just try and fail and then again put another diverter, another trial. We cannot let that happen. So we need to be pretty much confident about what we are doing. So one brilliant idea is create local turbulence. So when the plasma is spilling out from the closed surfaces, what we are proposing is create a turbulence after it spills out in this space, in the between this Bracken space, create a local turbulence, and so that when the plasma will come out and touch the metal vessel, it will not hit the vessel in 1 millimeter. So we need to do something so that the plasma spreads, be more turbulent, and actually spreads. And then what will happen when the plasma will fall, the per unit area heat load will go down. But this is hot magnetized plasma, so this is pretty much different from fluid turbulence. So we need dedicated codes, etc. As I said, I'm advertising our group's current research. So we have in our theory, what we are trying to propose is the turbulence broadens the heat load onto a wider region, wider area on the diverter. Thus, the per unit area heat load on the plates decreases. It's not the solution. Of course, the material science research need to be done so that we can produce better materials for the diverter. But still, at least if we can spread it on, instead of 1 millimeter, if we can spread it on 5 millimeters, it will be within the range. Typically, the space available is 5 to 6 millimeters. However, the scaling of the diverter heat load profiles with the shape and size of the tokamak is highly nonlinear. You can't just do some back of the envelope calculation and predict it. It's not that easy. This creates a pressing need for the comprehensive ab initio numerical simulations to achieve improved plasma confinement with existing tokamaks. Or if you want to build some more tokamaks in your future. Now I think you can see that this is the, imagine this is the tokamak, this surface is somewhat like that. And our simulation region is this red region that's here. So this is our simulation region. So this is the outside of the main confined thing. So think of it as when there is a turbulence, think of it that this whole yellow surface is like vibrating and plasma is coming out from here. So we are only concentrating in one single sector here like this. So this is coming out from here and only this much is available. After that, there are like other diagnostic things and etc. So we need to create the turbulence, and we don't want the plasma directly to go and then touch this vessel because there is no diverter here. So we actually need the plasma to come out, spread, but not that something that it touches here. It should follow the magnetic field lines, and the diverters are somewhere at the bottom or in for different configurations, either at the top or bottom or both. So if we have, let's think we have only at the bottom. For the typical purpose of Aztecs, it's in the bottom. So the plasma should actually follow the magnetic field lines. The magnetic field lines are like this, exactly like this, helical. They should follow and like come down and hit only at the diverter region, because we put very expensive metals or materials at the diverter only, so that we know that okay, plasma will come out only at the diverter, and we don't want the plasma to touch here. In future, whatever I'm going to talk, so you can see, I will make a coordinate transformation. So this helical stuff will be actually unwrapped. So all the in future, all the movies and everything you will see in this XYZ coordinate. But always remember, it is actually that wrapped thing. It's not just this thing. So the simulation domain is actually wrapped. I will unwrap it and then present things like this. Okay, so it's this effectively. This part here, this region is the core region. So this is the geometry you can understand. So these are the magnetic field lines, the helical magnetic field lines, and these are typically the filaments that get generated, and they travel outwards like this. Yeah, so these thin red line, that's the magnetic field line. You can see this is helically wrapped. This is a very thin magnetic red magnetic thin line. This thing, and you can see there is a thick magnetic blob or filament that is written here. Filament. This is. These green things are basically the filaments that is coming out. So this is basically this is technically called the edge or the spray pop layer region. So the filaments actually come out and they should travel more in the radially outward direction. These are all plasma filaments, and this should travel in the radially outward direction and then come down, following the magnetic field line and hit the diverter region. So diverter is here, you can see. It's written here. This is the diverter. So whatever it is coming out, so this is the core where the fusion happens. It should travel outwards like this. And it should come out from here and then follow the magnetic field lines and should hit this diverter region. This is the diverter region. Okay. Yeah, so there is a separatrix. So this is like this. There is a separatrix. And we are doing a very simplified helical geometry here. No X points and nothing for the experts. And yeah. But how we are simulating? We are simulating very simple things. We know the Vlasov equation. So this is just the Vlasov equation, electromagnetic. This is the Poisson bracket. It's a modified Poisson bracket in presence of magnetic field. If you have a self-consistent magnetic field evolution, it's non-canonical. Effectively, it's a non-canonical coordinate system. So the description of the Poisson, the definition of the Poisson bracket gets changed. but effectively it's the similar. And you have one more term here. This is the magnetic vector potential. So overall, this is just the Vlasov. This term is a collision term, and if there is a source, we have a source. So, and this is a distribution function. R is, that's free space. Here we have a different coordinate. So we have radially outward. One is radially outward direction, another is the helical direction. This thing wrapped around. And we have a binormal direction, which is kind of the polar plus the magnitude. But roughly, it's you can take it as radially outward, helical, and just perpendicular to both of these. And if it were pure Vlasov, you would have 3 velocity coordinates. But we are doing gyrokinetics. So when we have gyrokinetics, we reduce one of the velocity coordinates. So V parallel is the parallel direction with the magnetic field. And since they're charged particles, so they just rotate at a very fast rate. So mu is the magnetic moment. So this is the definition. So if you have the magnetic moment, it's like half m v park square by some normalization v at that case. So we get rid of one velocity dimension here in gyrokinetic stuff. It's a huge reduction of simulation cost. So that's why gyrokinetic is so much celebrated field. So we have extended it for electromagnetics because this definition and all this stuff are newly added. And since ages people were doing delta F theory, nobody had done full F electromagnetic gyrokinetic earlier. This is the first sort of result with continuum full F electromagnetic gyrokinetic theory. Delta F means you have a distribution function. Here the F is the full distribution function. Earlier people used to take a Maxwellian distribution and deviation from the Maxwellian. So that's the F plus F Maxwellian plus delta F, and they used to simulate just the deviation. But you can see that here things are pretty much turbulent and pretty much violent. So it's assuming or specifically in presence of elms, there is something called elm in the edge localized mode, etc. Assumption of this delta F stuffs are not really good. So it's better to simulate with full F. It's more computationally expensive, but it's probably okay. This is the standard Hamiltonian half m v square basically. If you substitute this, it will be half m. So plus some electrostatic potential. And now if you just do some little bit of algebra, you gain this equation. And we solve this equation in some helical kind of coordinate. So that's it. And the algorithm that we are using is pretty much familiar, probably all of you, is discontinuous Galerkin. So it's that. And what we are actually doing, so we have a tokamak. We know this here. So he knows more about it. He works there. Called Aztecs. They have improved version Aztecs upgrade. So in the Aztecs upgrade tokamak, we take the numbers from the experiments there. So they have a lot of very painstaking and beautiful experiments. So we take exact numbers from the experiment, and then, like for example, the magnetic field strength, the major radius of this torus, minor radius of this torus, and the location of the where the plasma is coming out of the closed field lines, density of electrons, etc. All this temperatures and etc. And we feed it in our code, and there are not many. In our code, there are not many tuning parameters. It's just the numbers that we take from the experiments. And we give the information only at the separatrix region. So separatrix region is basically, I don't have a picture. Okay, so you can take for circular kind of geometry, this yellow surface is the separatrix region. It's a little bit different, but anyway. Just as zeroth order description. So from this separatrix region, the plasma is coming out. We give the inputs only at this separatrix region, and then we try to predict things for the rest of the simulation region, and we compare it with already experimentally measured data. So this is a view at z equal to 0. So you have already seen this movie. And earlier people used to do electrostatic simulations, and you can see now the magnetic fields are actually vibrating. For aspects, it's not that important, but when we will simulate for ITER, going for full electromagnetic simulation will be very important. So you can see the density blobs that are coming out from here, and they actually basically shear off from this and propagate radially. So this is the radially outward direction. So they propagate in the radially outward direction, this one. So this enhances the turbulence in this scrape-off layer region. So this is called technically the scrape-off layer region. And this essentially reduces the diverter heat load. So this is the diverter heat load here. And diverter heat load gets reduced if you have more turbulence here. So we need a more flat profile in the diverter so that we have the per unit area. This is the major radius. So per unit area, we don't want very high heat flux in these regions. We prefer same amount of heat should come out, but it should be more flat like this. So these are the experimental measurements in the tokamak, and these are the numerical simulation. Of course, they are not one-on-one, definitely, it can't be. But they are roughly the order of magnitudes are close, both for electron density, ion density. So these are the averaged profiles of electron and ion temperature. The numbers are close. And then we need to find theories, how can we make the simulation region more turbulent? So there are several theories on blobs, and so these are called the blobs. This one, like the densities, long-lived density structures that come out from this turbulent region, and we need to make theories like how can an experimentalist do things so that the blobs will propagate farther in this experimental or simulation region. We need to allow the blobs to propagate more in this direction so that the diverter heat load gets reduced. Reduced means per unit area, so that we have a flatter profile. If we do not have that, we'll have more heat in this radial region and less heat here, which is bad, definitely. So there are already a lot of theories for that. Okay, and you can see so like this. So it's still not very much turbulent. It has the plasma is coming out. So this is the core region. So you can think this is the radially outward direction. So this is in meters. This is 2.1 meter and 2.185 meter, 145. So 0 is somewhere there. So that's the core region. This is the radial view. And the very hot plasma is coming out. And we need to tune the things such that we can prescribe the experimentalists to do experiment in that way so that these blobs propagate more in this region. And as I said, there are many theories of how to produce the blobs and etc. so that they propagate well. And there are experimental measurements on these individual blobs' velocity from Aztecs for the same shots. So we take the shot number and simulate for them. And we do simulations, and we try to go as close as possible for the experimental observations, and we try to make theories. So this is not a phenomenological theory. It's something that we earlier do the theory and try to predict. And if that holds, then only the theory is valid. Otherwise, the theory is failed. So it's a challenge. Interesting. And you have the measurements of the heat profile, heat flux on the diverter coils in the experiment. So these are some measurements for different collisionality, etc. And we do in Jekyll in simulation, we also do that. And we try to compare these two things and try to see like how close are we able to reach towards this experiment. So first thing is like we are building the technology, simulation technology, so that we can replicate the experiment. And then we'll have to find more parameters so that we can actually have more flat profile, and then we can go back to the experimentalists, talk with them, suggest them that you do this, and if they do that, if that is successful, then only our theory is successful. Otherwise, it's not good. Summary: making fusion commercially available is a necessary. It's not a luxury, because it's the hour of energy crisis. So within 50 years, there can be some issues. Out of several other challenges, solving the age issues, because more or less in the core part is understood, but age turbulence and age physics is important. It's most essential as a for me, I think. So earlier, our simulation capability was not there. So experimentalists already have a lot of insights, but computational methods are actually cheap and becoming more reliable. So, and when we are actually building such machines, like a few billions of dollars we are spending to build one machine, it is important to do a predict first era, predict first technology, to perform a predict first technology. So in simulation, you do that, you predict it. And if everything shows, like if everything comes up properly, then you tell the experimentalist to do that. Otherwise, you will lose a lot of money, right? So you can't allow to do like, well, yeah, failure is the pillar of success, but it's not always, if it is a very expensive one. But we already have the technology to predict things. So the era has already begun. So we have to take simulations very seriously. And we have done an electromagnetic full F gyrokinetic simulation using some computational plasma. This is a discontinuous Galerkin computational plasma framework that captures the essential features of strip-off layer turbulence for experimental parameters close to aspects of it. The next thing we can do is do more parameter scans and etc., and find more flat profile and go back to people here in the Aztecs and tell them and do this. That's it. And I acknowledge the whole JP team. Gregor, Thomas, Vladimir, Dominic, Andreas, Frankenko from IPP.
Great. Okay, thanks, Rupak, for exciting